Ladies and gentlemen, our program will now begin. Please welcome the CEO of Churchill Club, Karen Tucker.
Thank you so very much. Thank you and welcome. It's great to see this crowd out here tonight. Hope the rest of the people will join us here in the room shortly. Our discussion tonight is called The Renaissance of Silicon. The genesis of this event was when Kirsten Bordner talked to us about possibly doing a treatment around this topic. She and her team had been talking about it, and they were speaking about a new semiconductor industry transition to accommodate an increasingly diverse set of end markets, such as cloud computing, automotive, artificial intelligence, and others. Then along came our 21st annual Top 10 Tech Trends event in May, when Navin Chaddha from Mayfield, who is here with us tonight, posited the #1 top trend, as voted by the audience of 400, which stated, "The renaissance of silicon will create industry giants. With the end of Moore's law," Navin explained, "new semiconductors are required for a cloud-native, data-dominated, AI-powered IoT world. The rise of these new players will put silicon back into Silicon Valley." That brings us to this evening. We're all here to discuss and ponder this topic, thanks to Micron, and 4 distinguished experts have joined us to weigh in. Simon Segars of ARM, Victor Peng of Xilinx, Sanjay Mehrotra of Micron, and Tammy Kiley from Goldman Sachs. Thank you all so much for being here. Tammy has graciously agreed to lead the conversation tonight, but we have asked her as a subject matter expert to also weigh in on the conversation herself with her insights. Appreciate that very much. If this is your first time attending a Churchill Club event, I'd be pleased to provide just a brief introduction for you. Founded in 1985 and kicking off with our very first speaker, Bob Noyce. Today we are the premier independent thought leadership platform devoted to encouraging innovation, economic growth, and societal benefit. We look for what's new, next, not widely known, and try to hone in on opportunities that today's trends represent. Before we bring up our speakers, there is one more thing to say, and that is that the hashtag tonight is simply Churchill Club. Let's now give our warmest welcome to Victor, Sanjay, Tammy, and Simon. Thank you.
Now I'm on. Great. Well, welcome, Navin. This is all your fault that we are here today. No, thank you. And it's an honor to be here with such a great group of people. So I'm Tammy Kiley. I'm a partner at Goldman Sachs based out here in the Bay Area. And what I just thought I would do is set the stage a little bit for the conversation that we're about to have tonight. I have one caveat, though, which is there are obviously lots of things going on in the industry and more broadly from a geopolitical perspective. And I think what you won't hear is a lot of time and discussion on that topic specifically through some of my Q&A, largely because we really did want to focus this conversation in and around technology and innovation, and so that you'll see a bit of that coming through as we go through. So since we are sitting in the middle of Silicon Valley right now, I thought I'd start with a random Silicon Valley fact. You can use this at your next cocktail party, which is Silicon Valley's moniker has actually been around for almost 50 years now. It was actually first called Silicon Valley by the then CEO of Ion Equipment Corp., Ralph Verst, and he had actually used the term in an interview with Electronic News, and it stuck. And so we've been sitting in Silicon Valley, which is now known for lots of other things beyond silicon, for almost 50 years. And if we think about the evolution of the industry backdrop and what brings us to where we are today, if you look at when some of the semiconductor data really started being collected in earnest, so from 1984 to the year 2000, the industry actually grew at a compound annual growth rate of 14%. And now, 14% nowadays is difficult to achieve on a compounded base for that given point of time. And if you roll the clock forward from 2000 up until 2016, the next 16 years, the industry actually grew at 3% compounded. We were pretty much GDP. And so that really brings us to the conversation that we have here tonight, which is what comes next in the industry. And I'm really excited here to be with this panel. And if we think about what Karen had said early on, is there is a lot of very interesting trends that I'm really excited about in the industry as go forward. You've got the advent of artificial intelligence. You've got the growth in cloud and hybrid cloud computing. You've got increasing electronification of automobiles. You've got the emergence of trillions of connected devices through IoT that will be further powered by the growth in 5G. And so there's a lot of exciting things happening, but with the backdrop as well of some of the more technical challenges from a manufacturing and price performance perspective with Moore's Law. So with that, what I'd like to do is just actually have each of our panelists just introduce yourself more formally. I suspect that everyone in the room knows all of these folks, but Sanjay, if you'd like to start off with a quick intro.
I'm Sanjay Mehrotra, President and CEO of Micron. I've been with the company now a little over 2 years and extremely proud to be associated here with Micron. I consider it a national treasure, an iconic company, and really exciting opportunities for the company ahead. And I assume you'll give us a chance to talk about the company a little bit later as well, right?
Sure.
Okay.
I'm Victor Peng, CEO of Xilinx. I've been with Xilinx for 11 years now. I took over as CEO for about a year and a half ago. I think Xilinx is a really unique and special company. I had the good, fortune to work in CPUs, GPUs, and now FPGAs. So I really think I've kind of worked in the sort of the holy trinity of semiconductors here, and I'm really excited about where semis are. I think it's a really exciting time. I say that sincerely after 37 years in the industry. I really think this is a golden era. So look forward to the discussion.
And I'll be asking you more about that. Good, Simon.
Evening, everyone. I'm Simon Segars. I can beat you all on tenure. I've been with ARM for 28 years. I became CEO 6 years ago. All these trends that we've been talking about just briefly here, really exciting to us. We are driven by innovation that goes on in the semi industry, the devices that people bring to market, and helping try and solve the computing problems that sit within those. All of these market trends you're describing need more processing capability, and that's what gets us out of bed in the morning.
Great. Well, we'll start off with the first question, and I'll start, Victor, with directing this at you. People are saying now that the semiconductor industry is experiencing a renaissance, and I haven't heard in my 20 years of Goldman semiconductor and renaissance in the same sentence. What's going on that you think is making people view the industry this way?
Yeah, I think you alluded to a few of those trends already. It's like, it really is. I find it kind of amusing that there's still sort of a debate. I mean, Moore's Law has run out of gas. I mean, and now what I'm understanding is some people look at it as, I want to talk about traditional Moore's Law. So I'm really talking about scaling, right? Dennard scaling and also 2D shrinking that has run out of gas. That really is profound, even though we're so used to hearing that, because that really is what has made all of us accustomed to as consumers. Every year for the last 40, 50 years, things get better, faster, cheaper. And that's not a physical law, right? It took, collectively over time, trillions of dollars to make that happen. So that's one big trend. The other big trend is what you said. I mean, the numbers keep going up. We've talked about intelligent connected devices for a long time. It's really happening, right? It's certainly hundreds of billions, maybe trillions over time of intelligent devices. And now intelligence also means one or multiple forms of artificial intelligence in these devices. And these devices are everything from IoT, or what I like to use as a phrase of endpoints, to the edge, right? And edge could be a server form factor, it could also be a car, right? And then in the cloud, whether it's public or private, all of that end-to-end is becoming smart, intelligent, generating zettabytes of data, most of it unstructured every single year. And in order to sort of crunch that data and make it useful information, right, you need, factors more performance. So, the Renaissance is driven by a burning necessity, right? Like when, things like architectures that have been honed over these years, and you look for like little optimizations that get you 1% here, 3% here, that plus, whatever, you might get 20, 30% in a new generation. You need tens, hundreds, 1,000x kinds of improvements in compute, bandwidth, and storage over the next 10 years. You're not going to do that with the same architectures. So I think the Renaissance is going to be the fact that there'll be new architectures. And when I say architecture, I mean at multiple levels. At the technology level, like transistor, device, and things like that. Packaging, advanced packaging, integration, microarchitecture, instruction set architecture, and even architecture at the scale of entire data centers, right? So a lot of people much smarter than I say, look, the entire data center is a computer. Right, it's going to be heterogeneous computing, and there's going to be computing near the CPU, near the storage and memory, in flight, in the network adapter, or even in the switch, And I think, there's just so much opportunity, and that's why I think there is going to be a renaissance.
That's great. Thank you. Sanjay, would you like to add your thoughts?
I've been in this industry for 40 years, and I have never seen more exciting time in these 40 years. And I'm going to address this specifically from the point of view of memory and storage, which is where I have spent my career in. And when you look at where the markets for DRAM and flash used to be, 10 plus years ago, it was much more about, of course, the internet age and, mobile devices, smartphones and PCs. That's where the applications were. Now they have become much more diversified. Today, the end markets are certainly in data center, cloud, as well as enterprise. We are in smartphones, we are in networking. Our memory and storage solutions certainly are in PCs and new supercomputer applications, as well as IoT devices, autonomous vehicles. All of these are great, well-diversified market opportunities. What that is driving is unique requirements for each of these markets too. So what used to be like commodity solutions, now they're becoming very application specific as well. Smartphones, you need a lot of low power DRAM. You need high performance combination of DRAM and flash in one package called multi-chip packages. These are creating unique differentiated opportunities. Automotive, we like to talk about it, opportunities in the future as data center on wheels. I was just at Baidu in China about a month ago and actually took a ride in one of their autonomous vehicles, and it had more than 1 terabyte of storage in the trunk of the car and more than 100 gigabytes of DRAM in the trunk of the car as well. So indeed, data center on wheels. These are kind of DRAM and flash capacities that used to be in servers really not too long ago, right? And even today. So that's what is exciting, that unique differentiated requirements, whether it is related to performance, high bandwidth memory in data centers, or related to low power applications, which actually now are really spreading all across the end markets. Think about sensors. We talk about IoT, and think about sensors that will be on the shelves in a grocery store through a camera monitoring, what is happening with inventory on the shelf, and when does the shelf run out of space? Out of the product is trying to sell. That will have AI engine in it. It needs to have very low power capability so that it can last on battery life for 2 to 3 years. So it's really driving new applications on the low power side, high performance, high bandwidth, reliability, quality. This is very exciting. It's creating more differentiated opportunities for memory and storage than what we had ever seen in the past. And of course, the renaissance is also being driven, as Victor mentioned, new kind of architectures, because you're going to see more and more compute move to the edge. And that will require closeness between memory and storage, as well as compute will be good. This leads to new architectures, and these will be data-centric architectures, unique opportunities for us. So we are very excited in working with the entire ecosystem of our end market customers, as well as ecosystem partners, in creating new differentiated solutions that actually will start driving greater and greater relevance for memory and storage, greater and greater value for memory and storage, and that's the renaissance in memory and storage for you.
That's great. Simon.
Yeah, I think we really are at a different period in time for the tech industry as a whole. When I look back over the last kind of decade, 15 years, a lot of the driver of growth was the growth of mobile. And I think if you go back about 5 years, the industry was in a bit of a lull. And I can remember discussions with industry peers at events where people were kind of going, mobile's going to slow down pretty soon, and I don't know what application comes next. And then all of a sudden, there's this kind of combination of effects, and it's the delivery of really high power computing in the cloud. It's the delivery of really low power computing in handheld devices and in IoT devices. It's bandwidth. It's lots of things that kind of come together at once, coupled with fundamental algorithm development, have now led to a period where you go talk to people and it's like, well, there's 5G. That's now a thing, and it's going to consume silicon. Right. There's AI as a broad trend that's going to affect everything. There's IoT. There's autonomous vehicles. There are all these things suddenly as new drivers of growth. And because of some of the constraints that exist through the run out of Moore's law, it means you have to work harder. to come up with something that delivers more performance at lower power and lower cost than you did last year. There's no kind of freebie from optical scaling anymore. So you have to work harder at that. The applications are there. Raw compute power and performance is there. It's creating an environment where actually it costs less to innovate than it ever did in the past on the application side, and that's a driver of fundamental technology underneath.
That's great. Simon, so we'll move on to the next question for you, and this is changing gears a little bit and being a bit more specific. Sanjay had mentioned the movement of the industry towards more application-specific devices, generally speaking, or the need for more heterogeneous types of devices to address different applications. One of the trends that we've been following has been the emergence of companies that you haven't historically associated with the semiconductor industry starting to have their own semiconductor development. So obviously Apple was very early on this. We've got Google, we've got Alibaba, and many others who are now taking on more ASIC type approaches in their businesses. And what's your view on this? Do you think this is something that is the start of a trend, or do you think this is a pendulum that will ultimately swing back towards more standard products over time?
I think it's a trend for sure. I think some of the drivers of that trend are the desire for more performance and the need to optimize the solution for the application that you're looking to address. It's driven by scale in some cases. You look at the hyperscale cloud players, they buy a lot of silicon, they're deploying a lot of silicon. The algorithms that they might be using are quite tailored to what they do. And so if they can find ways to optimize the silicon for maybe something that only they do, then why not do that yourself? However, we know painfully that the complexity of building semiconductors is not for the faint of heart. And so it's highly unlikely that people are going to be building...
I think the audience agrees with you on that, by the way. So.
Highly unlikely that any OEM is going to start building all the chips that they could possibly want. So it's not for everyone. Big cost involved. But I think there's going to be a number of players that do this for those various reasons. I mean, look at the chip that Tesla built recently. I mean, that has got a lot of compute power in it. There's no off-the-shelf product that they could have put in that did quite that, because they're looking to solve a problem that many people are trying, but nobody has actually ever solved before. And so are looking to match the software and the hardware together to create something more efficient. Sanjay, you mentioned the work that somebody like Baidu's doing. You open the trunk of one of those cars, and it is a supercomputer on wheels. That's great if you want to make 10, but if you want to make millions of those, you've got to scale it down, and that's going to require a lot of innovation. And that's the kind of problem that people are looking at and thinking, well, can I come up with some different tailored solution? But as I say, it's not going to be for everyone. I think the merchant semiconductor market's going to exist at least until I retire. But you are going to see people...
We're not letting you retire,
yeah.
I suppose. So.
You're going to see people looking for different ways to innovate.
Good. And so, Victor, obviously, this is an area as well that you have an interesting vantage point on. How does this affect your business?
Yeah, so first of all, I want to drill into a point, Simon made that I want to amplify, which is that, people have a need to optimize and customize, right? And why is that? One, we talked a lot about, you need factors, tens, hundreds, even 1000x factors, but it's not just in performance, it's in performance per watt or per energy. And you need to do both. You need to hit that absolute performance, but you also have to improve the energy efficiency. So to do that, the problem is general purpose solutions have a problem because by definition, you give up a lot of that optimization because it's general purpose. So I totally agree. In order to get that amount of not only absolute performance, but also performance efficiency, you need to optimize things more. ASICs is one way to do it, and I think there's a lot of, in fact, in this sense, then we'll be a panel and have a little bit of controversy, is that's just an implementation or a path to do it. We, as you know, many of you here are familiar with Xilinx, invented the FPGA, but we move well beyond the FPGA. The whole issue is that there are other ways that you can have the same impact of what would be a customized piece of silicon, now optimized for specific algorithms, indeed, problem domains, this new thing of domain-specific architectures, which we might touch on later. But I think that's how you can get those factors of 100, even 1000x, because you're not trying to solve a general problem. The thing with ASICs, though, is you're literally solving a very narrow band of problems. So if you kind of go and say, general purpose processors is completely DC to, very, microwave, you can see, ASICs are really like just a direct line of sight, rifle shot kind of thing. And I think what we provide with it, originally in our history, FPGAs, and now these new scalable, adaptable platforms we call ACAP, I think we hit the nice sweet spot by getting factors of performance over a CPU, but it's more, adaptable and customizable without having to spill silicon. So back to how's it impact me? It doesn't really, because I think our products do hit this unique value proposition that other fixed architecture type products don't, or purely software programmable products don't. Our products are both programmable software as well as programmable at the hardware level, which means that you can change the very hardware architecture itself, and you can in fact change that on the fly. So I think that's a unique value prop that's actually increasing in value given the way the next wave of computing is going. I would also point out that, again, back to what Simon said, what you need for an ASIC or any very fixed function chip is you need some degree of stasis, right? So that means, the problem you're trying to solve has to be stable enough. If you have to interface with standards, those standards have to be stable enough because it takes a while to implement and execute that. You also need quite a bit of capital in dollars, as well as quite a bunch of really expert people, not only at the silicon level, validation, software, and so forth, and you need about 2 to 3 years, truthfully, end to end. And I think there are people that have those capabilities and have the economics to sort of justify that, but I think that's going to become more and more exceptional when you look at the next 10 years out as opposed to the mainstream things.
Good. Thank you. So Sanjay, the next question I'll have for you, and if we look over the last few years, we've seen a lot of consolidation in the semiconductor industry. I think CapEx started first, capital equipment's followed, now we're really seeing IC consolidation. So the top 15 IC providers last year comprised about 70% of all of the semiconductor industry. And so if we look at the implications of that, how are you seeing the effects of consolidation in two ways? One, from the overall economics, and then also from the sources of innovation. What's your view on that?
So I'll share the experience at Micron itself. Micron, over the course of last almost 20 years now, a little over 20 years, has driven tremendous amount of consolidation in the DRAM space. And certainly today, it leaves us as the only company in the Western Hemisphere that actually is a designer and manufacturer and a supplier of semiconductor memory and storage solutions. And certainly, over the course of these 20 years, technology complexity has increased tremendously. Capital intensity has gone up substantially. You require scale in order to meet the requirements of the customers, as well as to be able to produce the products in a cost-effective fashion. And of course, the R&D intensity has gone up so much that you need scale to really get ROI on all the R&D activities. So consolidation, clearly, given the increasing complexity that really has been underlying the R&D, the CapEx intensity, all these aspects absolutely drove the consolidation and actually works to the benefit of the industry. It helps us meet the requirements of our customers because customers absolutely expect companies to be able to keep pace with R&D, keep pace with innovation, bring in new solutions to the market faster, and of course meet the requirements in volume. So I think consolidation is a natural byproduct of the changes that have occurred with respect to increased complexity, capital intensity, etc. What I'll also say is that it gives us the ability, and it gives larger companies certainly have greater ability to invest in future innovation engines, to be able to make certain big bets. These increased complexities really take now several years to really judge whether they have the right long-term potential or not. And that really is a game for larger companies as well. Of course, that does not take away from the innovation that smaller companies can create. And that's why a company like Micron actually has a $100 million venture fund that enables us to be having a front row seat with the startups that are really driving innovation as well. And give us opportunity to see how our innovation agenda aligns with the innovation agenda of the startups as well. So I do think that this trend of innovation definitely has made the industry stronger and a stronger partner to our end market customers as well.
Got it. Simon and Victor, would you tend to agree?
Generally, yeah. I mean, I think it's scale. Well, it's economics that drives this. The cost of taping out a chip on 5 nanometer is astronomical, and the cost of porting all the IP and getting a design flow in place and just doing it once is really, really high. So unless you can amortize those costs across multiple designs, frankly, nobody's going to be able to afford to do it. So, I think we're going to need large semiconductor companies doing multiple designs on those advanced nodes to keep the progress of the kind of raw semiconductor devices progressing. So I think that's a thing that helps drive innovation. Of course, the more expensive it is, the fewer people can afford to do it. But unlike other industries, we talked about the steel industry. I don't think innovation is going to completely dry up because there are just too many other factors. And the fact, especially because software is running all these devices, there are too many other factors pulling applications through that mean that we're going to have to keep innovating at the silicon level.
Yeah, the only thing I want to add that's a little different, I do believe you need scale, but there's different ways in which you get it. So for instance, the way we get scale is because we're so flexible with the exact same piece of silicon, we could serve not only different use cases, but completely different industries. So we aggregate our volume over multiple industries and multiple different applications with the exact same piece of silicon. And I would also say that this thing of a customization too. So I could sell the exact same piece of adaptable programmable silicon to two head-to-head, full-on, all-out competitors, and they will implement different architectures. So on the other hand, if the way you get scale is here's the fixed application, and you need that home run, like you're the next dominant applications processor in a mobile handset, and they're all the same kinds of things because everything's standardized. That's a good way to get scale. That's great, right? But again, as I said, definitely need scale because the investment cost is huge, and you got to amortize that. But there's different ways you can get scale.
Good. Well, I like the optimism there. Simon's steel comment was I was in Taiwan a couple of weeks ago, and I had one unnamed company's CEO say, I'm convinced this industry is going to look like the steel industry in a few years, and to which I was somewhat mortified, but glad that we have points to the contrary here.
Where do we begin?
Exactly. Good. All right, so Simon, back to you. And switching gears a little bit to software. Mark Andreessen a few years ago was quoted as saying that software is eating the world. And what's your reaction to this? And how important is software, the software ecosystem, to what all of you are doing?
Oh, absolutely. I mean, it is the ability to turn hard problems into software, which is what has been enabled by the advances in computing. Has been a huge factor for driving innovation. It's enabled applications and all sorts of analyses that you just couldn't have done before. When I go back to when I started my career, and when I learned about programming, which was actually long before I started my career, it was really hard. You had to write assembler. You maybe had a C compiler. Compilers weren't very good. So the complexity of the code wasn't very great, and you couldn't do much. Now, because the underlying compute power has gone up so much, you can write at much higher levels of abstraction. That drives productivity. It just enables you to get a lot more done and just experiment in ways that you couldn't have done 30, 40 years ago. So it's a huge driver of innovation across our industry, and it pulls through some of the other things that we do to support that underneath. I think what's interesting though is what's going to eat software. And I think that's data. The way in which applications get developed, I think, is going to change. We've been discussing this internally within ARM about how, especially even in the embedded space, where you think about, when people think about AI, they think about generally running big applications in the cloud. That is all moving to the edge. Right. And the way you develop software for embedded applications is going to change. And it's going to change because we're moving to a world where software can now extract patterns out of data. Algorithms can evolve themselves, problems can get solved in completely different ways. And I think that's going to just change the way we think about problem solving with hardware and software. That data element, I think that's going to eat up. That's going to be the next thing that's got a heavy appetite.
I like it. Good. So, Victor, next one's have you lead off, there's been a lot of discussion about what comes next after Moore's Law, such as more specialized processing, 3D architectures, new memory technologies, et cetera. And looking ahead, what do you think are going to be the most interesting areas of innovation or even interesting areas of disruption over the next few years?
Yeah, so you heard me already kind of somewhat foreshadow this. Like, I think the way you can get factors even like, literally like 1000x is by, instead of trying to solve everything, right, you narrow the domain. Now, I don't think you should narrow it down to exactly one use case and application, but you narrow the domain. And now you can optimize an architecture for that domain have some degree of bandwidth and customization or whatever differentiation. But I think so. The term is domain-specific architectures, the DSAs. So I think that's going to happen in multiple different places. I think. So you kind of preserve that programmability, but you can get those factors. I think the other interesting trend that you're going to see is, again, computing. I would sort of stand and say, head, like, in one sense, the traditional architecture, whether this is data center or embedded devices, there's a CPU-like thing someplace, and it's doing most of the processing. Then there's memory and storage-like things, and then some connectivity-like things. And they all just stayed in their lanes. Now, as I said, I think you're going to have computing near the storage. You're going to have computing, different kinds of computing offloading the general purpose CPU, something heterogeneous architectures, whether it's machine learning or something else. Even the connectivity, right? There's AI in networks, wire to wireless interfaces, and switches. There's going to be intelligence in switches, not just programmability in the control plane, SDN, but also in the data plane. So that's the other trend. And then I think, again, back to this notion, and clearly we have a viewpoint on this, is that if you're going to scale something out to literally trillions, that needs some adaptability in it. It's I say this all the time. Broad systems that are proliferated like that, just like natural species in the world, needs adaptability for resilience, and because it needs to change when the needs of the environment of the marketplace changes. So if you scale out like a bazillion kind of devices, you don't want to have to change those out, right? When there's a new application, there's new neural networks that are actually more important that you couldn't have predicted, or they're new standards. Right, so I think the additional thing in the future, I believe, is some form of adaptability and flexibility, not only from a software perspective, but at the hardware level. Because software is great for productivity and interoperability. It's massively wasteful in performance and power efficiency, right? All those layers of abstraction, you're burning cycles and cycles, and you're burning storage and other things, right? So I think those are some of the big trends.
and that very factor, I think, is one thing that makes embedded software development so different from what you might write in the cloud, where you've effectively got infinite computing, and who cares if it's inefficient. Doing that in an embedded device, that's remote, that you want to deploy and never ever touch again. There's a really interesting, I think there's interesting innovation to do in that trade-off of what's fixed, what's flexible, what's truly programmable, what might be semi-programmable, what's reconfigurable. That trade-off, there's no one answer to that.
Yeah, and but you just said it too. It's like this whole thing about software is eating the world. But I really look at it this way: what does software eat? It eats data. How does software convert data to really something useful? Information. It has to process it, right? So what's enabling a torrent of real-time data? Semiconductors. What's enabling it to crunch it, so digest that data? Semiconductors. What's going to enable it to store it and retrieve it and move it around in the networks, wire to wire? Semiconductors. So and I think the big wake-up call is we've forgotten that, because this thing called Moore's law has kept letting people just throw cycles and cycles of things away because they want one more layer of abstraction. Now it's like, it's not going to be that easy, right?
I would agree with Victor that while software may have an opportunity to eat the world, but semiconductors definitely get the first bite, and they absolutely get a large share of that bite. And yes, software gets it too. And again, when you think of IoTs, right, and billions of devices, connected devices, and the intelligence in those devices, basically, every square inch of this planet will be a source of data that will either help us understand life or change life, find solutions to the biggest unsolved problems of the world, or enrich the lives of the consumers, the people, or find new business solutions around the world. All of this absolutely needs data, and it's exciting for us because that data lives in the kind of solutions, DRAM and flash, that Micron makes. And yes, with respect to Moore's law, certainly there have been challenges over the course of last several years. Actually, our industry, memory and storage, Moore's law has been less relevant for last 10 years. Cost reductions have reduced. Gigabit gains coming from each technology transition has lessened over the course of last 10 years. But if you look at the industry, actually it has thrived. It has thrived through tremendous innovation. For example, in flash, what used to be 1 bit per cell moved on to 2 bit per cell, and now everything is 3 bit per cell, and Micron actually late last year, announced 4 bits per cell of solutions going into SSDs. So engineers have a way of finding solutions. I'm excited about the opportunities ahead. NAND has gone from 2D to 3D. We are in the 4th generation of 3D NAND, which is now in production at 96 layers. And in the future, we are looking at 200 plus layers in not too distant a future of NAND. DRAM has gone through architectures of stacking up multiple devices in packages, as well as tremendous disruptive opportunities and architectures for DRAM as well in the future. So a lot of innovation happening, both at the memory technology, DRAM and flash, but it's not only limited to that. I think combination of DRAM and flash is creating new solutions. As I mentioned earlier, multi-chip packages in smartphone, automotives, etc. So that innovation is absolutely continuing. And new kinds of memories. You all have heard about 3D crosspoint kind of memory in very early stages of development, but other disruptive memories will come along too. And certainly all working toward data-driven compute architectures and opportunity to bring compute and memory and storage on perhaps over the course of next several years when we talk about 10-year horizon on the same chip as well, I think. And so just think about how much energy is wasted in bringing data to the compute engine. Now, if it all can be in one chip, it absolutely results in tremendous efficiencies, and it results in performance that is highly power efficient as well. And that's what is going to be needed for the world of IoT in the future, and of course driven by AI and connectivity like 5G and beyond, and of course all the aspects of cloud computing and all the end market applications.
Good, thank you. And so, as Sanjay mentioned, one of the themes being the more closer alignment of memory and compute. Thinking about what comes next in compute as well, Simon. I gave Simon the zinger question, so we'll let you talk as much or as little as you'd like. But what do you think about quantum computing?
I think that next time I'm on a panel like this, I shouldn't be on vacation. We have the call.
This is what happens when you miss the prep call.
So quantum computing is really interesting. I happened to be at a talk recently where a professor from the University of Innsbruck was describing how quantum works. I'm sitting there going, I get that. Okay, now you've lost me. But what's really interesting about it, though, is it's going to enable computing, solutions to problems that you just can't solve today. The exponential nature of the number of bits or number of states that you can represent through qubits, as you add more and more to them, means that you can get to a scale of being able to process data that you just can't do today. So with a few hundred qubits, you can start to do molecule analysis and simulation, which require a number of bits equivalent to the number of atoms there are in the universe. So you can't do that on a conventional computer, but you can do it with a few hundred qubits, which is interesting. The problem is you can't build a few hundred qubits today. You can build maybe a few, and they're not very stable and they're not very reliable, and there is no software development environment at all. This is not a case of rewrite the back end of your compiler and suddenly your application runs on a it is not like that. Quantum computing also is not a replacement for today's computers. Your cell phone is not going to have a quantum computer in it anytime soon. Quantum computers are going to be, the size of this room, a conventional supercomputer sitting next to them to feed them, and a whole lot of plumbing and physics going on to actually make it work. Right. But the class of problem that can be solved, as I say, is different, and it isn't anything that we can do today. One of the challenges of that is how do you simulate whether it's going to work or not if you can't simulate it using a conventional computer? So there are so many unknowns, but the underlying technology, which is getting better, once it is delivered, it is going to enable some new things, and that's going to be really interesting to watch. But we are 10 to 15 years away from any kind of delivery of that in a form that's going to be kind of useful on an industrial basis.
Thank you for taking that one. Good.
I'm actually going to Simon tomorrow to learn about
exactly. So maybe I'll move on just to our last question, just to make sure we've got time for Q&A. We can all ask Simon more quantum compute questions. So we're sitting here today. Roll the clock forward 5 years. So we're sitting in 2024. What do you think this conversation is going to be like in 2024? Sanjay, I'll start with you.
I think by 2024, think of 5G, how much it really, and we are just starting with it, how much it really would have changed the world in terms of enabling faster connectivity. Think of AI, how it would have really affected, so many applications, so many end markets, and of course, would have changed the lives of everybody. And its applications in healthcare and industrial applications and financial markets and, every walk of life. So all of this, when we are sitting here talking about this in five years from now, we will probably be looking at, boy, how much has 5G changed our world, how much AI has started to really emerge as a real revolution in our lives. And we will certainly be looking at, how we are able to derive so many more insights from the data. And, what kind of new architectures will exist in the future. I'm sure that will be an ongoing discussion 5 years from now as well.
Good. Victor?
Yeah, I'd say similar. I think that some of these things that are now in development will be deployed and really will affect people's lives. I'm glad you mentioned healthcare because, we have customers doing everything from genomic, simulations for diagnostics and also simulations of treatment protocols. Intuitive Surgical is a good customer of ours, and so they do, in the loop, automation for non-invasive surgery. They better clinical outcomes, better quality, of course, and actually reducing the cost of healthcare. And we're in endoscopy, so there's a lot of that. I think when you get factors 100, 1,000x, right, that not only is going to create economic value, and as you said, things like infrastructure, whether that's communications infrastructure or computing infrastructure, not only is that going to create that value, but I think the other thing is if we're successful at reducing the power consumption, that is an existential issue, I believe, in terms of climate change, right? I heard a statistic recently that, data centers are now on order of 10% of the global worldwide power, right? And when you look at, just even training and the computes that you want to use for training, and when it's just in the early days of AI training, let alone inference, that's already in single-digit percent. So, that can't scale an exponential and be sustainable, right? So I think there are many people here who are in semiconductors or in systems or software or investors. I think it's not only a huge business opportunity, I think it's also to a degree a moral imperative that we actually make that happen, right? Like find those 1,000x kind of improvements. And that's why part of the reason I think it's so exciting to be in the business right now, right?
Yeah, I'd agree with you completely. I think climate change as a driver of innovation is something that we're going to see really be a thing over that time period. Well, one other thing I'd say just on 5G, I get asked a question a lot. What's going to be the killer app for 5G? And I don't know the answer to that. I'd like to think in 5 years' time that is maybe become obvious, and it would become obvious because the technology will get rolled out, it will get put in people's hands, and people who aren't in this room, or maybe they are, will start to innovate and find those answers. And then maybe on this panel we'll be talking about what's the killer app for 6G, because I think there might be a panel on that at Mobile World Congress next year.
Oh.
These things will be coming at us.
That's great. Well, good. Well, thank you to panelists for all of those and for letting me put you on the spot like that. So now I know we've got just a terrific audience here, and sorry I've been facing this way. Hi, folks over here. Perhaps we turn this over now for Q&A towards the panelists, not me. Thanks.
No, you're a subject matter expert.
Yeah.
Yeah.
I know you.
Yes. Oops. I apologize.
What's the case for being optimistic about climate change when we have Moore's Law slowing down at the very time when we have this insatiable demand for data centers and the Internet of Things and all that?
Well, I think some of it is down to innovation. The approaches we were talking about at the beginning around creating different computing engines to solve things in a more efficient way. If you just take a big honking CPU and run lots of code on it, that's really power inefficient. As the algorithms develop and the silicon develops, to enable them to be run more efficiently, then you can get a lot of power out of some of these big applications that are going to get run in the cloud. So I think innovation on computer architecture and microarchitecture is going to help get power down.
Yeah, I would sort of say, when you need things like 100x, you don't fiddle around with the same markets. You start all over, right? And that's what you need, right, to make that difference. And in fact, if Moore's law kept going, the problem is we'd all keep trying to chip away, getting 30% a year, and you wouldn't like rethink the entire problem. And I think again, you have to think systems are hardware and software, right? It's a false sort of dichotomy to think of it, oh, there's just hardware and there's just software. It's really it's a system which is hardware and software, and you have to think system-wise, and you have to think complete new solutions and architectures. So.
And at Micron, we are doing a lot of work in terms of coming up with new memory solutions, which will be reducing power consumption, picojoules, per gig of transitions. And this is going to be absolutely essential in all end market applications, whether it is in your autonomous vehicles of the future, or it is data centers to help them reduce power. And ultimately, power efficiency and driving that at acceptable performance that is needed for the applications will absolutely be key in terms of really making sure they are cost effective as well as scalable applications, and they do tie in with the aspects of climate change as well.
Okay, next question.
I have a question for the panelists. Simon, primarily for you, and then want to hear the views of others. We have seen the success of alternative architectures like ARM in mobile, IoT. Talk a little bit about what's happening in the server world, because if x86 is over, but the innovation which is happening by Apple and other people on these phone devices, right? Like you're getting processing power at a fraction of the power of what the data center uses. So what do you think is the future of the data center and the server market? If x86 architecture and Moore's law is towards an end, and this is not an ad for you, I'm just trying to figure out. Maybe it is like Renaissance Silicon, right? Like this is ARM into the server and the data center market, right? It's been tried many times, so what's different? And would love to hear your views on how the architecture of the future of the data center and the server looks like in the next generation, and it might impact what Micron is doing also in that market.
Yeah, I mean, the way we look at this is about performance density. How much compute power can you get in a cubic foot, meter, whatever you like, of a data center? How much compute power can you get out for the amount of energy that you put in? How can you minimize the heat dissipation and spend more driving the computers than you do the air conditioners? What a number of our partners have done has been to build really innovative silicon, integrating lots of functionality with a processor, building that in a really dense way to deliver high-performance computing. You can see that today. You can log into your AWS account and run workloads on an ARM CPU, which costs a lot less than the other options that you have. So that is delivering real savings there. But I think kind of back to the earlier question, that the long-term evolution here has to be to think about workloads, has to be to think about what is the optimal architecture, which might not be an integer CPU with a floating point on the side. It might be dedicated engines for different types of commonly executed tasks that do things in a more efficient way. And it's kind of back to this trade-off of dedicated hardware, which is always the most efficient, versus complete flexibility. And you're going to need to come up with some happy medium between them to deliver the performance in a much more energy efficient way. So for us, we think it's about creating different flexible solutions. In many cases, an FPGA sitting alongside, that's now being commonly deployed in different data centers to allow specialist algorithms to run the workload split between a CPU and an accelerator.
Yeah, I think it's well accepted that the future of computing, whether it's a data center or even like endpoints or edge, is heterogeneous computing. I mean, CPUs are definitely not going to go away, and for certain single-threaded kind of applications, you still need improvement. But you're definitely going to have different forms of compute acceleration because these workloads are more parallel in nature, and you're going to, when it makes sense, absolutely compute near the storage. And this is how you're going to not burn power moving data that doesn't create any value. It just burns information, and it slows down throughput. And I also think, like I said, is you're going to see, computing as data is being moved through the network, whether it's smart NIC or even switches. And again, I believe that you don't really want to do a lot of specialized processors, because again, you have this problem is that may have been the state of the art at one point in time. It's an exponentially changing world. Like, you have to get those problems exactly nailed. What you really want is a different level of virtualization at the hardware level, and you want to be able to do computes wherever it makes sense, near the storage, near the network, or near the processor if it does need to be coordinated near the processor.
Data center for memory and storage is a huge opportunity. In fact, over the last couple of years, it has been one of the fastest growth drivers for demand consumption in data centers. And if you look at data centers, memory and storage, greater memory and storage is absolutely enabling greater value of the offerings that the large hyperscale customers are providing to their end customers. In fact, AI-driven servers, which today represent a sliver of the total server population in the data centers, less than 5%, are expected to grow to about 50% of the servers by 2025 timeframe. And what's exciting for us is that these AI servers actually require 6 times more DRAM and 2 times more NAND compared to the standard server. So this is a huge opportunity, exciting opportunity, and they require high performance, they require low power, they require very high reliability, and these are all the things that we excel at, and we are strong partners with them, and we are excited about the opportunity ahead. And when I said it enables greater value, you just have to look at AI server-based offerings by AWS are more than an order of magnitude higher in pricing compared to standard server offerings. And memory and storage is a key element. And if you look at data centers today in terms of hardware, 50 to 70%, of course, depending upon the cycles during the memory industry, is all going toward memory and storage, right, in terms of their hardware spend. So it is really a pretty powerful force for our industry, and I think it will remain so for next many years.
Next question.
I'm Jim Handy. I'm the memory guy. And so I should be throwing a softball question at Sanjay, but I'm going to skip over you. And I'm going to ask Victor something, challenge you on something. You assert that Moore's Law is dead, and yet there are increasing numbers of companies who are buying EUV scanners. And there are companies that have roadmaps out, 7 nanometers, 5 nanometers, and beyond that. And so how do you reconcile that?
Yeah, a few things. First of all, EUV is actually helping with removing some of the complexity of all these multi-patterning and stuff like that, but it isn't necessarily going to get us something beyond 3. By the way, 7, 5, 3, those are all marking numbers. Like, they used to be that number correlates to something physical or even somewhat quasi-physical. Now it's just like marking numbers, like 5 is, smaller than 6 and 7 and whatever. But I would also point out that, remember, performance, power, and area. We're sort of like, we've changed transistor architecture multiple times. No one's fixed the interconnect delay problem. And by the way, in interconnect, I also mean contacts and everything. So, you can get 1 out of the 3. It's really, really hard to get 2 out of 3, depending upon how hard you work and what kind of application you have. Getting 3 out of 3, I would challenge anybody who says they can get 3 out of 3, like in the good old days, which we thought was hard, but was the good old days. You could take an architecture, go to the next node, you got faster, better, cheaper, right? That's gone, right? Now, by the way, I think people expanded the notion Moore's Law to integrate, to sort of talk about other forms of integration, and we've been doing that. Since 28 nanometers, we've done silicon interposers with TSVs and all that kind of good stuff, and HBM, and we've integrated analog monolithically as well as in other forms. But that's not traditional Moore's Law, right? And I do think, 3D, if you could dissociate yourself from the 2D scaling problem, then absolutely you can keep going. But that's not traditional Moore's Law, right? So that's how I would look at that. But in any event, I'm not also saying that people still won't do something. It's just that there's fewer and fewer people that have a business case, let alone the expertise to sort of pull that off. And this gets back to the full circle about scale and everything else, right? So anyways, there you
So
go.
Jim, even though you didn't ask me the question, but since you asked about EUV, I have to comment here. I can't let that go. We have a roadmap in DRAM that goes from 1X to 1Y to 1Z, and then to 1 alpha, 1 beta, and 1 gamma in terms of continuing to scale the technology, continuing to get more gigabits per wafer, continuing to reduce the cost, all without EUV. And this is, Micron over the 4 decades. And really, I should also mention, Micron over 4 decades, 40,000 patents. I mean, just imagine in 40 years, 40,000 patents is like 3 patents a day. Tremendous amount of innovation. And one of the areas is that advancing with multi-patterning, cost-effective ways of producing DRAM and not requiring EUV until it really becomes a very viable, cost-effective, high-production technology. So you can do scaling without EUV as well.
Great, next question.
Hi, Samir Kumar from M12, Microsoft's venture fund. So this question is for Victor and also for Simon. So if you think about ML inference at the edge and at the low power edge and trying to trade off not getting too specialized so you can stay future-proof, but you need to get maximum power performance, so you do need to think about domain specificity. How do you think about what is the outlook? There's so many ML inference ASIC startups that are popping up. What is their outlook? And how should we also think about FPGAs at the edge? I mean, FPGAs are not easy to program, so what is the outlook for making it easier to lay down RTL code? So maybe I can also think about FPGAs in an embedded environment and making that easier to implement.
So that's a great question. First of all, we are absolutely making it easier to program, and we have people who program in C, C++, even Python. And by the way, the other thing is I would sort of say is that we're not really just an FPGA company anymore, right? So we've gone way beyond FPGAs quite a while. Having said that, I'm not saying anything bad about FPGAs. FPGAs are in edge devices. They're in automobiles, right? Big time. We're in ADAS applications, in multiple vehicles, models. We're in the next level of ADAS as well as autonomous driving. At CES, Daimler-Benz, showed in-cabin kind of systems, and they're using multiple neural networks, right? So look, I think the thing is, what you're seeing is a typical thing when people are searching for something totally different. They're coming up with all these proprietary architectures. I think what's unique about not only FPGAs, but more importantly, this new product category we've introduced, ACAP, for Adaptive Compute Acceleration Platforms, is the fact that you could overlay a domain-specific architecture onto that, and now you can program, whether it's with the compilers we provide, or it's just you're doing APIs through library calls or things like that, and we have an ecosystem of people that build all that. And so you could actually not only optimize for a problem, but you could dynamically swap that in and out. So you could swap entire architectures in and out with the same piece of fixed silicon, dynamically depending upon modalities. So cars, let's talk about it. When you're driving forward, you need certain different ways to look at those sensors and process that, as opposed to when you're doing automated parking. And we have customers that are doing that, dynamically just swapping kind of what they need in their neural networks and other kinds of sensor fusion and things on the fly. I think that's really powerful, and I think that in the future you're going to see more of this use of adaptable hardware even at the architectural level.
Yeah, I think it's going to depend on the application. In something like that, where you can maybe afford a more sophisticated platform that can do those sorts of things, then there's a solution for that. In the case of a really low-cost microcontroller that might be running some ML inference algorithm, and what really matters is squeezing every last half cent of cost out of it, that's likely to become a more fixed function. But perhaps in something that's maybe a bit more disposable, and where maybe you've got control over changing the software and not so much the hardware. So you're going to have to accept there are trade-offs to make in where you sit on that spectrum of how much you want to spend on that hardware platform, for how much flexibility, for how much efficiency, et cetera, et cetera. So I think the future, we always say, is not one size fits all. There are going to be different implementation points. And it's all going to be about cost, power, area, flexibility trade-off.
Okay. Next question.
Yeah. Hello. My name is Willem de Lang. I've been involved in microprocessor development for a long time. I'm very interested in the future about the implementation of 5G. I hear the signal doesn't carry too long, maybe 200-300 meters, and then we need repeaters for sustaining the 5G network. Where are the opportunities for Silicon Valley companies to be at the cutting edge of the implementation and the jobs? Where do you see the future of Silicon Valley in this, implementing this?
Yeah, so I think 5G is actually really an umbrella of not only different standards but also different technologies. I think you're talking about the millimeter wave type things, right? And we are actually in those types of applications, and I think some of that is also massive MIMO. That's not really 5G specific, but that's being also talked about and how they're going to use that. And I think along with that is dynamic beamforming. Right, and people are also looking at even applying AI to that, right? So, absolutely, we participate in 5G in a very big way. In fact, this whole thing about ASICs versus other programmable types of capability. I'm with Simon. That's why I also say CPUs are going to be around, GPUs are around. The traditional FPGAs around. ACAPS, I think 5 years from now, I think we'll be talking about ACAPS, and I'll have to define it for you. But I do think that this need of finding the right balance between it's just laser focus and can't be changed that much, but it gives you for that particular thing the ultimate versus going completely to it's completely software kind of general purpose. And I really think this adaptability that we have is going to have more and more applicability. By the way, in terms of 5G, when we talk about integration, different types of integration. We've integrated high-performance analog, ADCs and DACs to cover the 5G spectrum, not at the millimeter wave, but everything up until the 6G, into a digital logic. And I think that's another form of integration that's not about Moore's Law, but that gives you a different kind of system-level integration, right?
Great. Okay, next question.
Yes, my name is Rob from HDMI Licensing. So it's fantastic that there's a renaissance in silicon, renaissance going on here, and especially in Silicon Valley. Seems to be favoring the very large multi-billion-dollar semiconductors, as you point out. The top 15 have 70%. Are we seeing or going to see a renaissance in startups, especially here in Silicon Valley?
Well, I mean, there has been, to the previous question, quite a lot of VC money going into some of these AI chip companies. And I think one of the reasons for that is because it's such a new area. I mean, AI has been around a long time, but the ability to actually implement it in silicon is kind of happening now for a variety of factors. So it's a little bit of an anomaly that so much money has gone into that sector right now, but it's quite hot, and it's quite encouraging to see some people at least coming back into this market to actually invest some of their money. But some of these application areas that we're talking about, the chips required are very complex. The R&D takes a long time. Just the R&D behind 5G is taking a long time. It's big companies that have got the deep pockets to make those investments for the long haul. So unfortunately, I don't think we're going to go back to the days where Sand Hill Road was handing out wheelbarrows full of money to people who wanted to build chips. I just don't think that's going to happen in the way that it has in the past.
And maybe I had the benefit of having a sneak peek at the audience list, and so and it looks like I know we do have a lot of companies here that are from silicon startups. Perhaps just a quick show of hands, because I think this would have been very, very different years ago. Exactly.
The ratio would have been the other way around.
Exactly.
I just do want to add that through that 100 million venture fund we have, we do see that there are startups that are forming or that have already been around for a while that are absolutely working on silicon aspects. Certainly everything that Simon said in terms of increased complexity, what is required to do silicon in terms of a design and the funding it requires is really very different compared to what it used to be in the past. So it is more challenging, but there is a lot of innovation happening even at the startup level. And again, a lot of it is tied toward, new architectures, new ways, again, compute and storage together, these kind of applications. So I think it's happening, but certainly not at the pace that it was happening when I had joined this industry 40 years ago.
And one thing I'd add to that, or go ahead, Victor.
Yeah, I just want to add, I think Xilinx is doing its part in a different way, in the sense that, as I said, is we allow people to create architectures and get the benefit to their customers or themselves and their application as though they've customized silicon, but they don't have to do tape outs. Right? That's the power of like an FPGA and going to ACAP, this adaptable compute acceleration, which has, by the way, a multi-core ARM SoC on it, full out, memory, caches, peripheral bus and everything. It has an on-chip NoC. It has, the next generation FPGAs, and it also has a new thing called the AI engine. It's a heterogeneous compute platform itself, and people could put their overlay architecture on top of that and innovate and give people the power of customized silicon, but not doing tape out. So in that sense, and someone talked about, we're definitely trying to make this more accessible to more innovators. And in that sense, I think we're coming out with a platform that will democratize, people customizing silicon, but not having to do, hundreds of millions of dollars investments, that 3-year time frame that I talked about to put out a 7 nanometer, let alone 5 or 3 nanometer kind of silicon, right?
And I do think the one thing I'd add, just from more putting my banker hat on, which I wear, is the fact that the reality still is, though, that the exit path for most semiconductor startups is still going the M&A route. And so I'd actually say that is another way where big companies will be benefiting, and there will be some startups that will be benefiting, because effectively, if you're a company having to manage to Wall Street every quarter, the ability to actually bring in talent in one fell swoop can be very advantageous as well. And so I do think we'll continue to see, related to that, an active M&A market, and and we're super optimistic that we may see some high quality IPOs out of this round. Next question.
Gentlemen, my name is Frederick. I'm with the state of Arizona, and there's been a big push in the state, but also other states, for smart cities initiatives. And are you working with governments at all levels to help them with that? And do you see greater collaboration as that goes forward?
Some. Depends where you are in the world. Again, so back to the question about climate change, actually. So smart cities and making lots of things smarter are a route to addressing some of the climate change issues, which may result in more energy getting burned in data centers to process all of the data that's coming from the IoT devices, but net, great benefits from that. So for us, it's a really interesting space. It's going to be something that does consume a lot of silicon. It's going to be something that creates a lot of opportunity for optimizations, for efficiencies, and it is going to create a lot of business opportunity along the way. There are lots of issues around the data privacy, who can do what with it, and there is not a lot of clear guidance on exactly how to deploy it. So who you work with to solve that problem is different in all different parts of the world. There's no standardization on that. So certainly we get involved to the extent we can on helping, as government policy white papers get written, we often get asked to contribute to that, and we certainly try and play a role in doing so. Sooner it happens, the better. So if we can help, defragment some of that, then it's all good from our perspective.
Great. So I think we have time for probably 2 to 3 more questions. So why don't we move to the next question?
So this is Shankar Trivedi. My question is, do you, given the explosion of demand for semiconductors for every application, do you have sleepless nightmares about the supply chain and the security of semiconductor, capacity of semiconductor manufacturing, or is this a problem we shouldn't worry about?
I would definitely say that semiconductor manufacturing today is extremely challenging, and that's why it's not a game for anybody else to easily get into. I mean, you do hear about sometimes, different companies, and people worry about, China getting into it, but this industry really has mastered its capabilities over the course of 40 years, and not easy for others to duplicate. And certainly the complexity, the challenges, the resources that are required, the talent that is required to manage it is really, really getting more and more complex and challenging every day. So I would not say I have nightmares over this, because we have a great history of over 40 years, and many leading companies in the industry absolutely have that capability as well. But what I can tell you is that it absolutely remains a top focus area for the company. Every day, running manufacturing operations absolutely requires that every second you are managing your operations and absolutely watching the metrics to ultimately deliver the desired output, the desired quality level, the desired technology mix, desired efficiency, desired cost structure. So it is a major focus area. It ain't easy, but Micron, through 40 years history, absolutely has all the capabilities built into it, and it really requires a highly skilled workforce, and we have that.
I mean, that's great for memory and storage, but what about compute and networking semiconductors?
Well, I mean, in terms of the semiconductor manufacturing, I mean, there are companies, well-established companies that are doing that as well, right? And those two have been around for a long time, and and I'm sure that those companies have their own focus area in this as well. But I'm sure you guys can add some.
Yeah, look, I mean, I do think one thing about Xilinx is over 35 years old. We have. The one thing about all this scale and complexity and surviving all the cycles and everything is that the people who are left are really good. And we work with the best, right? Like, actually, we're an ARM licensee, and we work together with Micron heavily, too. And I think, so I do think, like, the people who are left, like, the people who really, don't have true sustained excellence are not around, frankly, right? And I do think that, there is a huge amount of institutional learning, and I think that's why we can deal with some of these challenges and why I'm optimistic about the innovation of being able to take the next level of scaling to literally, trillions of devices over time, right?
I think one thing I'd add to that is the collaboration that goes on across the industry continues to impress me. I mean, I've been doing this for quite a while now, but it continues to amaze me just how collaborative this industry is. So it isn't a case of, Victor works on his own and creates a design, and he turns up and hands it over to Mark Liu, and he sends him wafers back through the mail. There's a ton of stuff that's gone on to make that happen. And, there is just a ton of industry collaboration that happens to solve the problems so that there can be predictability in what comes out at the end of the day.
Great. I think we have time for probably one more question. So the next question, wherever the mic is. Great.
All right. So the panel touched on a lot of hardware and software issues, and our industry has been talking about software, hardware, co-design. But one of the hurdles of deploying or driving heterogeneous architectures at scale is the software hasn't evolved, right? I mean, you look at, there is a reason why x86 is, most of the workloads are run on or more than 90%, 99% maybe, are run on x86. So what can we do as an industry to drive adoption or accelerate the adoption of heterogeneous architectures?
Well, I personally think, first of all, it's already happening. I mean, it's happening at multiple levels and in multiple ways. And I also do think, yes, x86 will always be there, both because there's still a huge body of software that's legacy, and when, fetching instructions and doing the execution's the right thing to do, and you'll still need improvements to that. But again, what's most of this data? It's unstructured, it's video, it's things like that, and that is not something that you want to use anything that just does a traditional, right, von Neumann kind of architecture. That's why machine learning is happening. And so what? So people created, ASICs or TPUs or things like that, a specialized architecture just for that. But you can't do a specialized architecture for every neural network because there are many neural networks, and there's many new innovations around neural networks, pruning and compression and all these other things. So heterogeneous is the only way forward. I do agree that in terms of scaling for more development to enable all these developers is important. But, and I think that's why there is multiple people, including Intel, working on APIs and things like that to try and target multiple different execution kind of engines, right? We, as I said, our ACAP is one chip, a multi-core ARM SoC, FPGA fabric, and an AI engine with a network on a chip on a single chip. So we are developing an environment that enables somebody who doesn't know how to do RTL design to tap into that kind of power. So yeah, absolutely. When that starts getting culturalized and proliferated, you're going to see a next wave of innovation, right?
I think there's two other things I'd add to that. One is software tools help abstract some of this problem away. So there's a whole lot of work going on to take an algorithm and then map it down to the different processors that happen to be on the piece of silicon that you actually want to run it on. And that in itself is becoming a much larger area of focus, how you go from the very high level of abstraction down to the transistors themselves. I think also it will take a bit of time for engineers to really get their head around thinking about the problems differently. I think 5 years from now, we will have gone through a shift where people just think about problems differently. I'm not just writing linear code that's going to run on a fast processor. I've got to use a heterogeneous architecture because of power or efficiency or performance, whatever. And it makes you think about the problem differently. But that will take time. That will take some relearning because most people are taught on a PC today, and you get what you get.
Great. Thank you.
All right. Thank you so very much for all of you for sharing your perspectives so candidly. We appreciate it very much. We do have a very small token of our appreciation for you, and it is, of course, the Churchill Club speaker T-shirt. Please wear that in very good health. I'd like to tell everybody here that a recording of this program will be made available as soon as possible, hopefully within the next 24 hours on our YouTube channel, where you will find recordings of most of our other programs as well. Hopefully you will find that to be a very useful resource over time. Keep an eye on the programs coming up. I think we're going to bring in Tom Siebel next month. On the 27th, we have our 8th annual Churchill event on September 12th. And so keep an eye on our schedule and come when you can. We would appreciate that very much. Now we have some dessert and coffee for you so that we can continue the discussion. So we hope you'll stick around for that. Thanks again. You've been a wonderful audience. Good night.